probabilistic analyses generate greater life years and Cowley than deterministic analyses in Markov models. This presentation is based on our publication titled as Comparison of the Expected Rewards between Probabilistic and Deterministic Analyses in a Markov Model. I thank my co-authors. There is an interesting phenomenon. Favorable results are often based on weaker evidence in probabilistic analysis. For example, a model input that uses a treatment effect derived from weak evidence, based on a small sample size, generally leads to misleadingly favorable results in terms of life years and Cowley in a probabilistic analysis. We illustrate this in an example below. We developed a simple Markov model that included three states: healthy, disease, and dead. All patients are initially in the healthy state, and only one-way transitions are allowed in the model. People can only move to worse health states and cannot move back to better health states. Thus, there are three possible transitions. 1. From healthy state to disease state. 2. From healthy state to dead state. And 3. From disease state to dead state. We assumed the transition probabilities are constant. We used the duration in the surviving states, life years, as the reward. We set the cycle length at 1 year, the time horizon to 100 years, and did not apply discounting and half-cycle correction. Using this model, we compared different treatments that have the same expected value of model inputs, but were obtained from the clinical evidence with different cohort sizes, 100, 1000, and 10,000. The distributions of model parameters are shown in the table. Now, let us review the findings. The Markov rewards in probabilistic analyses were greater than that in the deterministic analysis. The Markov rewards in life year were greater when the distributions of model inputs are defined from the weaker evidence. When the sample size of evidence was large, such as 10,000 people, the probabilistic analysis and deterministic analysis almost showed the same results. Furthermore, the probability of treatment with weaker evidence having a greater reward was higher than treatment with stronger evidence in the probabilistic analysis. This section, Jensen's inequality, describes the reasons for the above finding. Weaker evidence is associated with greater rewards. Jensen's inequality, named after the Danish mathematician Johan Jensen. If a function is convex on an interval, for all x1 and x2 in this interval and 0 is less than or equal to lambda is less than or equal to 1, the following inequality holds. This figure illustrates the concept of convexity using a simple geometric interpretation. If a function is convex, the graph of this function is below the secant line. Elbasher and Chatwell characterized the conditions for upward or downward bias using a three-state Markov model and derived rewards, such as life years, Cowley, lifetime disease costs, using mathematical expressions for transition probabilities. Further, the authors demonstrated that life years and Cowley are convex functions of transition probabilities using Jensen's inequality. Mercer then extended Jensen's inequality, as shown below in this slide. Based on Mercer's inequality, we can deduce that life years and Cowley estimated using probabilistic analysis are greater than those using deterministic analysis. Let x be the transition probability and function, x, be the life years in a Markov model. Let us assume that n samples are simulated in the probabilistic analysis, and let each simulation have the same weight and the sum of weights equals 1. When n is large, the left side of inequality represents the expected rewards in the deterministic analysis. The right side of the inequality expression is equal to the average reward in the probabilistic analyses in n simulations. Then, we can conclude that the rewards in life years and Cowley of a Markov model from deterministic analysis are less than those from probabilistic analysis, irrespective of the distributions used for transition probabilities. When model inputs are obtained from strong evidence, the parameter uncertainty is small and is concentrated around the mean value, so the rewards, life years and Cowley, derived from probabilistic analysis will be close to the rewards derived from deterministic analysis. However, if model inputs are obtained from weak evidence, the range of model inputs is wider, so the differences in rewards between probabilistic and deterministic analyses can be larger. Therefore, weak evidence generally leads to greater or equal life years and Cowley compared with strong evidence. Thank you.